Okay, so good morning, everybody. So just to briefly recall you what I was doing yesterday. So we discussed about the the probability distribution of the largest eigenvalue of a Gaussian random matrix, which I call lambda max, which is a random variable, and so this is a typical plot. So this is the average density of states, which is Wigner's semicircular law, with a SERP edge at √2. And so lambda max on an average is around √2, and it fluctuates around that on a scale of n to the power minus 2/3. And if you look at the distribution of the typical fluctuations around the peak, so that's given by this Tracy-Widom distribution. This is just a cumulative distribution. But as we argued, that this is a typical fluctuation, so it does not describe fluctuations of order, for example, order 1, much bigger than n to the power minus 2/3. And for that, we need to look at the large deviation tail. And in particular, this question that I started out with, that what's the probability that all the eigenvalues are negative? So which means that the probability that lambda max is less than 0. So that means you are looking at deviations of order 1 as opposed to order n to the power minus 2/3. So therefore, the Tracy-Widom is not applicable there. And we need to work out what is the large deviation tail. And always remember this toy example on the side of this coin tossing. And in the coin tossing case, this was Gaussian distribution by central limit theorem, distribution of the number of heads. And we also worked out the large deviation tail, but there it was a smooth function connecting the left and right large deviation tail. And but here, what you will see, what I'll show you, that here the function will not be smooth, and the left and right, it won't be symmetric. Left and right tail are going to be very different speed, large deviation tails, very different speed and very different behavior. And that is a sort of, the core of why there is a phase transition, because you go from one phase, which is characterized by the left large deviation tail, to another phase, which is characterized by right large deviation tail. And they are not smooth because the speeds are different. Okay? So that will be the sort of things. So but anyway, motivation-wise, the reason we looked at the large deviation tail on the left was because we wanted to answer this question. That is how we started out with. But then it turns out that this phase transition is sort of another thing where the large deviation function is not only useful, it's essential to understand this phase transition. Okay. So this is the second question, which is related to that why is Tracy-Widom distribution so ubiquitous, and why do we find it in so many places? And as I said, that usually we always associate universality with some kind of phase transition, where the microscopic details somehow become irrelevant near a critical point. And so the first question you asked is that can we sort of associate the Tracy-Widom distribution with some kind of phase transition, critical point? Okay. So it was not obvious in the beginning. Okay, you have just a PDF of something, and where is the phase transition? Okay, so so these are the questions we sort of posed, that where to look for a phase transition, and where is the critical point? What is the control parameter, for example, and what are the two phases? If there is a phase transition, there should be two phases. So what are the two phases? Okay, and as I said, for these to understand this, you really, the whole thing is hidden in the large deviation function, and that's why it's sort of important to study the large deviation function. So I'll just tell you basically what the main idea is, and then I'll go into the details later. So the main idea is the following. So the typical fluctuations you see is n to the power minus 2/3, and whereas if you look at atypical rare fluctuations, which are of order 1, much bigger than n to the power minus 2/3 for large n, as I said, they are not described by Tracy-Widom. And so what happens for finite but large n is that this width is of order n to the power minus 2/3, and then you will have these two tails. Okay? And as we'll see later, and as I mentioned, that the left tail, the speed will be n square, and we'll see the reason for it with some rate function. And the right tail, in contrast, will be of minus n, and with some other rate function. And the point is that the asymmetry of this is also related to the asymmetry of the tails of the Tracy-Widom distribution. And we'll see later, after computing phi minus and phi plus, that there is a smooth matching between the left asymptotic tail of Tracy-Widom with the left large deviation tail, and with this functional form, and similarly on the right. And because the Tracy-Widom itself is asymmetric, it has asymmetric tails, one side is cube and the other side is 3 by 2. So necessarily the speeds have to be different, but we'll see the physical reason for this. So now what is the phase transition? So this is about √2. So phase transition in the roughly speaking, so this is the picture is the following. So as you increase n, n goes to infinity limit, so the width of this region shrinks and goes to 0. Okay? So this whole blue curve here, it sort of gets collapsed onto a single point, if you like, in the n going to infinity limit. Okay? So all the measure is concentrated on the √2. It's like a delta function here. So the left and right tails, they are still non-zero, but they are extremely small probability. So as I said, most of the measure is concentrated here. But if you are plotting your PDF on a scale of order 1, okay, so you don't see this n to the power minus 2/3, it collapses onto a point. So on this scale, if I observe my PDF, I will see the left tail, a sort of point, and the right tail. Okay? And this is the, if you like, is the control parameter, and this is the critical point. Okay? And so the left side, so you have a left phase, and this is the right phase. So the left large deviation function is like the analog of the free energy of the left phase, which we call strong coupling phase. I'll explain this as I go along. And this right side, this will be the analog of the weak coupling phase. And because of this asymmetry in n square and n, so essentially what happens is that if you take the log of this and divide by n square, on the right side you have a finite function phi minus. On the left side, this will go to 0. And so essentially you have a sharp phase transition as you go across this √2. Okay? So this is the control parameter. These are the two phases. And so Tracy-Widom, if you like, if you zoom out this point, this critical point, and for a finite system and observe what is going on locally around that point, so it's like a finite size crossover function that actually connects the left and right large deviation function. Okay, so this is the sort of main summary of this picture, and then we'll see to expand it more. And so this large deviation principle, the fact that on the left side it will go like n square times some function, and on the right side it will go like n into some function. This was actually was sort of studied in the maths literature rigorously by Bengaluru and Guionnet. But they established the large division principle, but they didn't calculate explicitly this function phi minus and phi plus. And we'll see that how to compute them, and you need to compute them in order to really understand the nature of this phase transition. Okay? So, and as I said, the main conclusion is that there will be non-analytic behavior of this PDF as you go across this critical point. And there's a third order phase transition in the sense that I'll describe in detail. And this is sort of, you can find this in a review that I wrote with Gregory a couple of years back. Okay, so this is the sort of summary. This is the main picture. And then we'll go into the details of this. Okay? Yeah.
When you use the word order parameters, I guess you mean...
Sorry, say it again. When I use the word?
You use the word, or something that sounded like, on the left you have one phase, on the right you have
yes.
another phase. Talking about derivatives of phi minus and phi plus.
Yes, I mean, we'll see. I mean, okay, so I'll come to that precisely because there's a cumulative distribution, and then there is a, so if you like, yeah, exactly. So phi minus, you'll see in a minute, phi minus is actually the analog of, derivative of phi minus is the analog of pressure, because you have these charged particles, you have to push them to the light. So the pressure is non-zero when you go to the left, and the pressure is 0 on the right, basically. Okay. So what's the mathematical problem? Okay, so mathematical problem is very simple. I mean, so this is, let me just explain to you. So as we said, so we want to calculate this probability, that probability that the largest eigenvalue is less than or equal to W, which is the same event, that probability that all these eigenvalues are less than or equal to W. And we know the joint distribution of lambda 1, lambda 2, lambda 3, lambda n, which is given by exponential into this, this quadratic potential term, which comes from the Gaussian ensemble of random matrix. And then there's this interaction term between every pair of charges, if you like, which repels each other. Okay? So this is the joint distribution. And given this joint distribution, I want to calculate this probability. So what is it? So it's just a multiple integral, d lambda I. And this okay, so this I can write down as a ratio of two partition function, if you like. So the probability of this event is just, so the numerator is just this integral going from, this is not normalized, so it's going from minus infinity to w, because it's less than equal to w, okay? And divided by the normalization constant, which just goes from minus infinity to plus infinity. So in the numerator, you have, upper limit is finite at w, and the denominator upper limit is infinity, okay? So this is the main problem. You have a multiple integral to do. So everything, Tracy-Widom plus the left and large deviation tail, everything is contained in this multiple integral. Okay, so this is an exact thing for any w. Okay, so as I said, physically you can interpret this in the following way. So the denominator is like you have these charged particles with this energy, and there is no wall. Wall is at infinity, if you like, the w. So that's the denominator. So it's a free gas. Now in the numerator, I have a upper limit, which is w. So as if it's like you're constraining your charge system to the left of w. So this w is like a wall. It's not a physical wall, but if it's like a mathematical wall. It's exactly this analogous to the concept of tilt, because you want to calculate the statistics of the original measure, and to calculate the statistics, you actually put some effective potential, if you like, by imposing this wall. And so this is going to change the density because of the presence of the wall. So you calculate this new effective thing, the tilted potential, if you like, and then this is with tilt and this is without tilt, and the ratio of this thing is the joint distribution of lambda. Okay. So this is the main problem. Okay, we have to do a multiple integral in presence of this w. Okay. So how do we proceed about this? So first thing is that, here, the scale of lambda is of order 1, okay, always. So if I want to, get Tracy-Widom out of it, I have to really go near root 2 and expand on a scale of n to the power minus 2/3. And if I do that, then that's what Tracy-Widom did, and then you will get the Tracy-Widom distribution, okay? But our task is simpler because we are looking at order 1 fluctuation, so you don't have to go to this special, you don't have to zoom in at near the point, edge root 2. We can actually work on a scale of order 1, and there you will see that it's much simpler because you can actually evaluate this using a saddle point method. Okay, so that's the sort of main idea. So how do we go about doing the saddle point of this? Okay, so this is what I'm going to explain to you, and you will see that there is an entropy and energy term. Basically, main point is that you want to replace this multiple integral in the large n limit by a continuous integral of over functional density. And then you work in the continuous density language because it's much simpler in the large n limit and it gives you exact answer. Okay, so that's a sort of, so we'll remember this picture, and now I'll just shift to the board. So I'll do this, this general derivation here, and then we'll also see how, using the same method, you can actually calculate the distribution of a linear statistics that I mentioned yesterday, and. Okay, so our problem is, precisely this. So I have a multiple integral to do. Okay, you can forget about random matrix theory. It's just doing a multiple integral. So it's a very general method. And the point here is that this is a long-range system, so you can actually do basically mean field theory. It's already mean field theory in some sense. So this is the object we want to compute. So what's the main idea? So the main idea is to somehow, in the large n limit, is to replace this multiple integral, discrete multiple integral, with the discrete n discrete variables, to a continuous integral in the sense the following. So what is the idea? So the idea is, okay, so I have these point charges. Okay, there are lots of them in large n limit. So you can see that there's a roughly, in the large n limit, I can talk about a density function, okay? So this density is somewhere, some places it's high, some places it's low. So the average density, if you like, locally, in general, I'm not talking about the wigner semicircle for the moment, but, in general, this is just a coarse graining, basically, okay? So you have some density profile, okay? So, so the idea is that, so you can define an empirical density, which is for every, given configuration of lambda i's. So I can define locally this density variable. So this tells me what is the fraction of eigenvalues between lambda and lambda plus d lambda. Okay. I mean, this is mathematically strictly rigorous thing. It's not a function because it's a bunch of delta functions, but we'll not bother with the rigor here. And so this is the rho n lambda. And so the idea is that, okay, so you can think of, dividing your system into, so you're doing coarse graining basically, so you're into little boxes like this. So the idea is to do this multiple integral in 2 steps, okay? First, you fix a macroscopic density like this. So associated with this macroscopic density, there will be many such microscopic configurations, okay? So you have to sum over all such microscopic configurations, and then do an integral over all possible density functions, okay? So the 2 steps of coarse graining. So first, fix a macroscopic density. Lambda. Such that, you have a constraint that, it's not any function, it has to be a positive function. And it has to satisfy this normalization 1 because this is by definition, it's a normalized function. So I take all possible, density functions which are, positive variables and with normalized to 1. Then associated with each, for a given rho n lambda, now I basically sum over all possible microscopic and that's where the entropy term comes from, microscopic configurations of lambda i's. Okay. Because you can see, I mean, I can fix the overall density in each box, and then I can put this particle here or a little bit move around, so I have a lot of freedom to do that. And that's where the entropy term comes in. And then finally, integrate. This integrate is in the functional integral sense. Integrate over all possible rho lambda, satisfying the constraint, the normalization constraint that is. So this is the sort of main sort of program. And so mathematically, how to do it? I mean, it's just, okay, it's not that difficult. Okay, first thing before I do that, so there is this object here. So I can first write down this energy. So this is the energy associated with the microscopic configuration. So this is n by 2, summation lambda is square minus half log. So if I define my rho n lambda like this, so immediately you see that this will be n square by 2. Right? Because if you just substitute rho n lambda equal to 1 over n, this delta function, and do this integral, you get back exactly this summation. And this factor n here, n squared, n was already there, and n squared comes from this guy here. I multiply this and just do this integral. So this is exact. This term you have to be careful because here it doesn't include lambda I equal to lambda j. So when you go to the continuum limit, it's a little bit tricky because there's a self-energy term, so you have to put a cutoff. Usually you have to think that this is, in the continuum limit, this will be 2 lambdas, but then you have to put in a small cutoff a 0, which is like the 1 over the local density. not so that it doesn't diverge. So this is a cutoff thing, and okay, so there's a little bit tricky. I mean, okay, I won't go into the details of this, but okay, roughly speaking, so this will be, again, this guy I can write as and so this is the, when you put with the cutoff and put I equal to j, include the I equal to j term, and then take the continuum limit. So this is well defined. But then you have to subtract off the self-energy term when I equal to j with this cutoff. So there will be a cutoff dependent self-energy term, which will not write down in details. You can do it rigorously, but I'll not do it here. But only thing that matters is that, okay, this will be a order n term, essentially, because this is self-energy, there are n particles, so this will be a order n. Whereas these guys here are of order n squared, okay? So, okay, so the main point is that this energy of a microscopic configuration, you can write, entirely in terms of this macroscopic density, okay? So this part does not depend on microscopic configuration anymore. So they all have the, same energy. Sorry? Oh, okay, sorry, yeah. okay, no, yeah, good, you reminded me, okay. Okay, so this is the energy term, and so now let's carry out this program here. So I start with this integral Zn. Okay, here for the moment, we don't bother about this W, which will be in the density, will come later. But it's just doing general integral basically, okay? So what I'll do first, I introduce this guy, integrate over all possible rho n lambda, okay? And I stick in this constraint that this is the definition of microscopic configuration. Okay. So this object is 1 basically, right? You sum over all possible. Okay, you have to put this constraint also that. So I take all possible density functionals normalized to 1, and I just integrate them over this thing. So when I integrate them, this is just 1. But now I have this, the extra factor, which is beta of E of lambda I. Sorry. And then I have the integral over so I've not done anything. I'm just doing partial tracing. Tracing I have not done yet. I just introduced, so my original integral was without this factor here, okay? But I just stick in there because this is 1, okay? So I just do it like this, and then I'll just change the order of integration, assuming that that's allowed. So this is in the functional integral sense. And now the point is that this guy, as we just saw, that this actually is just a functional of rho n lambda. It does not involve lambda if I fix rho n lambda, this is already done. So I can take out from this microscopic integral here and write this as, E of rho n lambda. It's a functional. And then all I'm left with is this microscopic integral, which is delta function of rho n lambda minus 1 over n. Okay? And you immediately see that this is exactly the entropy. I mean, e to the power log of entropy, basically, okay? So this is just the entropy factor. So we can estimate what this entropy factor is, again by coarse graining. So roughly speaking, again, you think of this box picture, and let's say I put N1 particles in this box, N2 particles in this box, N3 particles in this box, etc. And I have a total number of N particles. So the entropy factor, this integral, roughly speaking, will be just how many microscopic configurations are there associated with a global density. So this will be just, N1 factor, just a multinomial. Okay. So if I have M boxes, and what is N1? N1 is just the local density times the number of particles. N2 will be local density in the box 2 times N, etc. So again, I can write down this as rho 1 n factorial, rho 2 n factorial, rho m n factorial. And now I can use this Stirling approximation for large n. And if I do that, so this will be exponential. So what is it going to be? Minus n times rho 1 log rho 1 plus rho 2 log rho 2. Okay. But this is just in the, now if you take the continuum limit, this is just rho lambda log rho lambda d lambda. Okay. So this is exactly the entropy here. I mean, this is e to the power minus n of this. So minus of this is just the entropy. And you see that the entropy term is of order n. Okay. So if I now put it back, everything. So this is, we have calculated that this is order n squared. So n squared times that integral, which I call, energy so this E, little e is just this object here. Okay, and then I have this entropy factor, which tells me this is rho lambda. This is, okay, rho has a subscript n always, although I've taken the large n limit. Okay, this, and of course, there is a, so this is the entropy term, e to the power minus n. And then we didn't write down explicitly the self-energy term, but okay, you can write down the self-energy term, and it will be of order n. I'm not showing this because it's a little bit long calculation, but okay, this is of order n. Okay. So both the entropy and self-energy term is of order n, whereas the macroscopic energy is of order n squared. Okay. So that's the reason why you see that you can actually, in the large n limit, you can actually neglect this entropy term. If your problem was a short-range problem, then of course this will be of order n, and this will be same order as entropy and energy. So in that case, if you want to calculate this, you have to minimize the free energy, okay, which is the energy minus beta times entropy. But in this particular long-range problem, entropy is just negligible compared to the energy. Okay. So this is the main, so you can just forget about this entropy term. Yes, no, for the Tracy-Widom, I mean, as I said, if you have to work on the Tracy-Widom, you have to really go into that limit, near w by root 2, w equal to root 2, and analyze this multiple integral in a completely different way.
You would rescale the lambda.
Yeah, you have to rescale the lambdas, okay. So then all these calculations will not work, okay.
You could still use that calculation, but now the entropy term would actually be included as part. There will be a trade-off.
Yeah, of course. No, there'll be both entropy and energy, both will be there when you are working in that limit. Okay, so this is the sort of, and now, what you can do one more thing. So how do we actually get rid of this constraint? I mean, you can just use the delta function. You can just use this integral representation of delta function. So I can just, write some d mu naught over 2 pi times, okay, so you have this functional integral. Forget these things. And then I just put mu naught times integral rho lambda d lambda minus 1. Okay. So this is just using the, I mean, or alternatively, it's just using the integral representation of the delta function. You can raise it to e to the power mu naught, where mu naught is in the complex plane, if you like. I mean, you can do a real space and then we do a weak rotation, but you don't care. So this mu naught is like a Lagrange multiplier, if you like, which enforces this constraint. Okay? And just to make it, this thing, so what I'll do is I'll just write this as beta n square and put a beta n square times mu naught, just so that it's of the same order, basically. So then this object here just becomes e to the power minus beta n square times this energy function plus this mu naught integral rho lambda d lambda minus 1. Okay? So, and then you have this. So now you see the saddle point is going to manifest. I mean, you can just minimize this object subject to this constraint here. And just to tell you that, if I have, just to make it connection, that if I have, if I want to calculate the linear statistics, as I defined before, last lecture, that something of that type. So if I want to calculate the probability distribution of M, given the joint distribution of lambda i's, all I have to do in this, large n limit, so you see that all I have to do is to do a multiple integral now over a d rho lambda. You have this, still this constant d mu naught over 2 pi, whatever, beta n square. You have e to the power minus beta by beta, okay, n square. Okay. And now all I have to do, this is the measure, and all I have to do is to, just stick in another delta function, which is m minus. And again, this sum here, you see that you can actually write this as n, okay, we have to rescale properly, and n times integral f lambda rho lambda d lambda. Okay, this is without rescaling, just this, okay. So if I, scale by m by n, so essentially this m by n should be, or just write it this way. And again, I can introduce another Lagrange multiplier, just replace this guy by its integral representation. And so all that happens, so remember the E rho of lambda was of this form, which is half times, whatever the potential was. In the case of Gaussian, it was just lambda squared, but in general, it will be some V of lambda. And then you have this interaction term, which is rho lambda prime, log lambda minus lambda prime, d lambda prime. So this was the original bare energy, okay? Then you have a term which comes from the first Lagrange multiplier, which enforces the condition that it's a normalized to 1. And you have there will be another Lagrange multiplier. I have to replace it by d mu 1. So this will be of the order, of the type mu 1, f lambda, rho lambda, d lambda. Okay. So if you look at the now overall thing that stays inside the n square, so all that happens is that you see this original bare potential. So now my, action here, so let me call this as S of rho of lambda. So what is the action if I want to calculate this distribution of the linear statistics? So the original action was that guy over there. So half, okay, there's no half factor. So if I call general potential, so in the case of Gaussian, this is just half lambda square, okay? Otherwise it will be some V lambda. So you have V lambda, rho lambda, d lambda minus interaction term. Okay, plus there is this first Lagrange multiplier, which is rho lambda d lambda minus 1. And then the second Lagrange multiplier, which comes from enforcing the delta function that the linear statistics is M, is basically this rho lambda f lambda d lambda is whatever minus m over n square, for example, or something like that. Okay. So what you see that now the action, so this term here modifies this effective potential. So this is precisely the tilt. So now you have a new effective potential, if you like, which is the original bare potential plus this mu1 times of f of lambda. Okay, this is just a constant term. So all you have to solve to calculate the linear statistics is the same problem as the original problem, except that your potential get tilted by this Lagrange multiplier times whatever you want to calculate. Okay? So I can calculate the linear statistics of the original problem just by changing the effective potential. Okay? So this is this famous concept of tilt, and this will be and this is so if you can solve the minimization problem with arbitrary v of lambda, then you can actually solve for any linear statistics. Okay? So this is the sort of main idea. And so let me now go show you how to minimize this action. Okay, so remember that effectively we have this, okay, let me first do it without any linear statistics. So I have this functional integral e to the power minus beta n square times this action. And this action is of this form. Okay? So clearly, so if there is a saddle point, then large n limit, this will be minus beta n square into the action evaluated at the saddle point density. Okay. So you have to find what is the saddle point density. So how do I find that? I have to just minimize this action. So if I take functional derivative with respect to rho lambda, so you will get from the first term, you will get v lambda here. And the second term, because there's a lambda prime, so this factor half will go away. And then you will have a Lagrange multiplier, mu naught equal to 0. Okay. So your rho star saddle point density should satisfy this integral equation for general potential v lambda. So in the Gaussian case, this is just lambda square. So how do you find the solution? So what is now you can check that you can see that this is just a condition of kind of energy conservation. So each charge, so this is the energy of the charge which is located at lambda because of its interaction with the other guys, and this is the external energy it feels. So this is just a statement of total energy is conserved, basically. Mu naught is like the minus of total energy. Now, first thing you notice, so for example, let's take the example of Gaussian, where v lambda is lambda square over 2. So I want to find the solution of this, okay? How do I find? So first thing you notice that this charge density, whatever that minimizes your integral, and if, for the moment, let's assume the w equal to infinity. So I want to derive the semicircular law from this, okay? So here the integrals are all from minus infinity to plus infinity in general. But the first thing you notice that, you cannot, for whatever the solution without doing anything, the solution, so if I'm plotting rho lambda versus lambda, it cannot extend over, all space, because this equation is valid, for lambda belonging to its support. Okay, whatever the support is, okay, wherever the charge density is located. But the point is that you cannot have the charge density spread all over from minus infinity to plus infinity, because you see immediately that for any potential that increases faster than log lambda, if I go to lambda, if it was extending all the way to, let's say, plus infinity, so there this guy is going like lambda square, whereas this term is going like lambda, log lambda. Okay? So you can never compensate, and this is just a constant, so you can never compensate this to make it 0. Okay? So this equation tells you that as long as you have a potential which is, diverging like faster than log lambda, as lambda goes to infinity, you can never have infinite support. So first thing we learned that it should be a single support. Okay? And let me assume that it's only a single support, that there is no multiple supports basically. So it will be between some A and B. Okay? So therefore, effectively, this will be from A to B. So this equation is valid for lambda belonging to the support AB. Okay, now I have to find the actual solution of this. So first thing what you can do is you can take, it's valid for anywhere in lambda belonging to AB, so you can take one more derivative of this. So if I take derivative with respect to lambda, so you get minus, here, okay, I'll write this and explain. So when I take derivative with respect to lambda, so log of this thing, when you take the derivative, it just becomes a principal part. You have to interpret this integral in the principal part sense, okay, because there'll be divergence coming from this. So this is the equation. And what is the physical meaning of this equation? This is just a force balance equation. So this is the effective force felt by a charge sitting at lambda due to all other charges due to interaction, and this is the force due to the external potential. And these two forces actually, balance each other. The two energies compete with each other to make an equilibrium configuration of the charge density. Okay. So this is the, so it's like, and here the problem is that you give me v prime of lambda or v of lambda, and I want to invert this equation to find the charge density. So in some sense, this is like an inverse electrostatic problem. Electrostatic problem usually, you give me the charge density and you want to calculate the potential, but here it's the opposite. And it's not quite electrostatic problem because of this, principal part here. And so these type of integral equations, they are called Cauchy's singular differential equation. And here, of course, the integral will go from the support A to B. Okay, so it's not obvious how to solve this. And in fact, if you look at any standard random matrix theory book, like for example, Mehta's book, which is a Bible in random matrix theory, so he writes this equation, and then he says, well, if you take lambda square over 2, so for the Gaussian case, this is just lambda. So then he says, okay, if you substitute the semicircular law here and do this integral, you see it satisfies this, okay? But it doesn't tell you, how to really get it for general v of lambda. But if you want to calculate the linear statistics, I need because I'm putting this extra tilt potential mu times f lambda, I need to know for general v of lambda, okay? So how do we solve this? This is where, and this was very useful for us because we somehow came across, it was not known very well in the random matrix theory literature when you started working on it. And we sort of came across almost by accident. It was known in the applied maths literature. So this solution of such differential equations explicitly was actually first worked out by Tricomi, who is an Italian mathematician, in 1957. Okay. So Tricomi actually had a general solution to this. So his theorem is that, okay, if you have finite support, assume that there is a single finite support A to B, which you don't know in this problem yet, but assume that there is such a thing. And if you have a general v prime of lambda, then the inversion of these rates, I'll first write down the solution explicitly. This is fine. So this is the exact answer. So whatever the arbitrary potential you give me, I can always invert this and and write it this way. This is a general solution. The proof of this is, of course, very complicated. You have to go through, all kinds of Riemann-Hilbert problem and so on. But let's take this solution as known. And then you see that, so so for example, let's look at the Gaussian case. Sorry? This inversion formula? Well, he derived it because, this is, in general, it's called the Riemann-Hilbert problem in mathematics, okay? So to solve this, you have to have all kinds of, complex plane machinery and so on. It's not so easy to derive this formula, okay? But for us, this formula was very useful because we could just use it to solve all these problems, lambda max in presence of it all. You see that if you have a wall, so then in that case, the upper support is fixed at W. Okay, you don't have to, B is not unknown, so W is fixed. Only the lower support is unknown. But in the free case, I don't even know what is the upper. I know that it has to be on a finite region, and all I know is that for the Gaussian case, it has to be a symmetric function. Okay, so B should be equal to minus A. But I still have, so symmetry of rho lambda tells me that B has to be equal to minus A. A has to be equal to minus B. Right? It has to be symmetric around the origin for the Gaussian case. Okay, and so I still don't know what the support A is, and I still don't know what this C naught is. Okay, but then you have two conditions, namely that your rho star lambda has to be normalized to 1. And the other thing is that because it's confining, so this rho star lambda must vanish, as at least in the free case, Gaussian case. So this should vanish as lambda approaches the support end. So you have these two conditions. So in the Gaussian case, where V prime of lambda prime is just lambda prime, okay? So then it's very easy to do this integral. I mean, you can do it by hand or you can ask Mathematica to do it, okay? And the answer is, so if you put back this, okay, and also you can, okay, in general, what you can show is that this C naught should be equal to A to B rho lambda d lambda. This is general, okay? But in our case, this is already 1 because of this constraint here. So this constant C naught is 1. Okay? So now if you put lambda prime here and do this integral, so I'll just write down the answer. So it's fairly explicit, it's totally explicit. For arbitrary A and B, just using this condition here, and that this is Gaussian, so this is the answer. And if you now use this symmetry, that B equal to minus A, so then you see that this just becomes, for B equal to minus A, this just becomes 1 over 8 pi square root of B square minus lambda square times 4 B square. Okay? So this is the exact answer, and now you have to impose the condition. So B is still unknown. I have one unknown still, and then you have to impose the condition that as lambda approaches B, this should vanish. Okay? But you see, as lambda approaches B, the denominator diverges, so you have to somehow cancel this denominator. So that means B has to be such that this guy must vanish when lambda approaches B. Okay? So that tells me that 4b square minus 8b square plus 8 should be equal to 0. So this gives you that b square is 2. So b is root 2. Okay? So this is the edge of the wigner semicircular law. And if you put b equal to 8, if you calculate this, you get square root of 2 minus lambda square. Okay? So this is one of the derivations of the Wigner semicircular law. But okay, there are many other derivations. I'll not do them. For us, this is good enough. Okay. So this is the sort of free problem, the denominator, remember. And now, I have to just solve it with numerator w here, right, when I have a wall. So if I put w, then, b is already equal to w. So you have this, so what you have is, okay, so there is a w equal to root 2. So this was a free problem. So your w was there. And so you see that when w is bigger than root 2, the solution will be always Wigner semicircular law, because, this charge density here, they don't see the wall. You're becoming the wall, but, they are already happy to sit over the semicircle. They don't see the wall, okay? So the solution for w bigger than root 2 will still be given by Wigner semicircular law. But you will get a different solution when w becomes less than root 2. So you're pushing your charges to the left. So what you would expect is that it should get deformed, the saddle point density, and, maybe it does this, okay? And so this thing, you can actually compute it explicitly. When w is less than root 2, all you have to do is replace the upper limit by w, b equal to w, and you have to insist that the solution should vanish at the, okay, you don't know what in that case, you don't use a and b. So a is some unknown, and b is w. This is your support, okay? So you have to solve this problem. But the potential is still, for Gaussian case, is still lambda prime. So the, solution is still this, okay? Except, so this is the general solution, except that b is now w, and a is unknown. And then you have to say that it has to vanish at lambda equal to a, so that fixes the value of a, and you get a new density. So you see the density actually changes. So saddle point changes only when w is less than root 2. If w is bigger than root 2, it stays the same saddle point as before. Okay. So this is the sort of main idea. So let me now get into the slides. Okay. So we have seen that denominator here, the solution average density is Wigner semicircular law, and now I'm just bringing this wall from infinity. So as long as w is bigger than, okay, so let me just repeat this again. So the denominator here, if you do the saddle point, and I just showed you how to do it, so you get the Wigner semicircular law. Okay, so you have this. Okay, so now I bring the wall, and the picture is the following. So when w is bigger than root 2, you see the saddle point density does not change. Okay, it's a Wigner semicircular law. Till you come to this critical point, w equal to root 2. And then if you push below the critical point, w equal to root 2, this new density is going to change. So this is the a, which I was calling, it will be some length which you don't know, which you have to determine. And you have to see what the charge density is by solving this Trichome equation. Okay. So this is the phase transition, basically. So let's see what happens as I bring w from infinity. So this is just to say that nothing will change. So if you, for example, as you put this, bring this wall w, and you monitor this cumulative distribution, which is the ratio of these two partition functions. So you see that when w, so this, remember, this is the cumulative distribution. So it should approach to 1 as n goes to infinity, and it should go to 0 as w goes to minus infinity. So you see it has to generally up this shape. So when w is plus infinity, okay, so wall is very far away, so this ratio is more or less 1. So I'm now plotting this cumulative distribution as a function of w for n large but not very large. So it's more or less stays close to 1 as long as w is bigger than root 2. Okay, so it's sort of more or less close to 1. And then moment w goes across the root 2, okay, you see that it changes immediately because you're pushing this gas of particles. So I bring this w. So this representative point is just moving. You see it was here when w is infinity, so value was almost 1. Then it will reduce a little bit. We'll see how to compute that. And as you bring in w further, so this thing will decrease, and then at some point when you hit the wall, you hit the semicircle. So now no longer. So this Wigner semicircle is stable here, but when you go there, wigner semicircle is no longer stable, it's unstable. You have to have a new density, and it changes to this form. So you're pushing these charges. So there will be a pile up of charges at the wall, okay? And so we want to know what is this new density. And so as I said, for W bigger than √2, it is given by the Wigner semicircular law here. But when W becomes less than √2, the deformed density, which is exactly, you just put this object, as I said, where A is determined, A is minus LW here, okay, minus L. So this is the new density, okay? And if you just put the condition that it vanish at this edge, then you determine this LW, which is exactly this, okay? So this is the sort of computation we did, a long time back in 2006. So you get exactly the deformed density, the new saddle point density. So once you have this exact density, then you see that, so this ratio, so now I'm talking about W is less than √2, okay? So what is it? So as we said, this upper object is just the energy evaluated at the saddle point with W minus the energy evaluated for the saddle point of W equal to infinity. So this is just the Wigner semicircular law, and this is this new density. So the difference in energy, so the cost in pushing this charge is precisely this large deviation function. So you just have to put this density back into the saddle point and evaluate this energy and compute this. So what you see is that this object then, because it's a ratio of two partition function, so clearly if you take the log, it's like the energy difference or free energy difference if you like, because entropy is negligible. And this is this has the interpretation of this left large deviation function is just the energy cost in pushing the Coulomb gas from its Wigner semicircular form. Okay? And so you can compute this phi minus just from the evaluating this difference in saddle point energy with these densities. And you can compute it explicitly. It has a sort of nice form here. Okay. And so it obviously now answers the original question I posed, just as an outcome, as a sort of corollary of this, is that if I want to know what is the probability that all the eigenvalues are negative, that is less than 0, all I have to put is, in this phi minus, I have to put W equal to 0. So if you put W equal to 0, you get back this number theta, which is 1/4 times log 3. Just comes from this. Okay. Okay, so very good. And other thing that you notice about this exact rate function is that, so if I plot this rate function, so remember this rate function is valid for W less than √2, okay? So if you plot this function phi minus of W versus W, so this is the √2, the edge. So, it sort of goes like this, and then it goes to 0 as W approaches √2, because when W is at the edge of the Wigner semicircle, it doesn't cost any energy, so phi minus W has to go to 0, and as W goes to √2, and it actually vanishes as a third power here. So this is it goes like, and with the prefactor, which is important as we'll see in a minute, is actually 1/6 √2. Okay, so this is the sort of picture of the left large deviation function. Now, what about the right large deviation function? So for that, you have to work a little bit, because, for the left large deviation function, you see, I was looking at the cumulative distribution, right? Which is this partition function of this. So now I'm setting W to be bigger than √2. So if I do this, standard saddle point that I'm doing, as we saw, that, when W is bigger than √2, the charge density, the saddle point density, is precisely Wigner's semicircular law, right? So Wigner's semicircular law is valid for all W bigger than √2. It sticks to the Wigner's semicircular law. So this ratio, if I do this calculation to this order, this will be, to the leading order, this will be 0, because this is both, the Wigner semicircular on both sides. So this will be 0. So then you have to go to the next order term. Okay? And when you go there, then you have to be careful with self-energy and all this entropy term and so on. But you can do that. But there's an alternative way of doing it, which is to say that, okay, instead of looking at the cumulative distribution, so this is a sort of excitations which are of order n. So you can ask, what is the excitation of order n, energy cost? So the physical picture is that, so roughly, So I want to set my lambda max to be at W. So I look at the PDF now, not the cumulative distribution. I say, what is the probability that lambda max equal to W, and W is bigger than √2 of order 1, let's say, okay? So typically, again, lambda max is fluctuating around this. So I'm now looking at deviations of order 1. So which are the configurations which is going to dominate, okay? In that, when W is much bigger than √2. So the configuration that dominates, this you can prove rigorously, but basically, I'm just telling you in words, is that so one charge is at W, and the rest of the n-1 charges, they sit in the Wigner semicircular law. So the configuration, so if you evaluate this object and write down this multiple integral and look at which configuration dominates, is the one where n-1 charges, they more or less stay in the semicircular form. But this one, you just pull out one charge and put it here, okay? So these configurations, okay, they dominate this multiple integral. And you see that why it's just, so then all you have to evaluate is what is the energy cost in pulling out this charge. And because this is one charge, so you're not affecting the other guys. So it's just the cost of energy is just the energy involved in pulling out this charge. So it's the interaction energy, the change in the potential energy that this guy feels being here and being here, and also the change of interaction energy of this guy with the rest of the n-1 guys, okay? And that's actually very easy to evaluate. So I won't do it in detail, but you just set, so you set this guy at W, one guy. So so if you evaluate the total energy, so this is beta, n square. Okay, let me not try to do the details, it'll take time. But you can do it carefully. And when you do that, so you see that this cost of energy, this is exactly the right large deviation function, phi plus W, and this is just the energy involved, just the energy of interaction energy of this guy with the rest of the other guys, okay? And you know the energy function explicitly, so you can evaluate. And okay, let me just do it. So if I just think of this configuration here, okay, and you have just one guy, so my action is my energy is lambda is squared minus the log of lambda I minus lambda j, I not equal to j. So basically what you're doing roughly, so this is the total energy. So of that, if I put in this configuration, you see one guy will be at W squared, right, this guy, and then you have a sum over lambda is squared. So I ordered the lambdas. So this is going from 1 to n-1, pull out the one guy. So this is the just the difference in potential energy. And here also I do the same thing. I write W minus lambda j sum over j not equal to n minus n. Okay. So this is the repulsion energy of this guy with the rest of the other charges. And then you have the other charges, their natural energy. Okay, so this is the total energy, I can write it this way. This is the configuration, energy of this configuration. But you see that basically, so these guys here, I can, all these sums, I can replace by and then whatever these energies. So the energy cost is just that involves only these W's here. So this is just the potential energy. So this is W squared plus, okay, there's a factor n here, so this should be n, plus the, okay, so this is, all right, so this is the, so these guys, so the rho lambda actually stays more or less in the semicircular form because you are just pulling out one charge, it doesn't affect the rest of the guys. So all you have to do is to look at the interaction energy, which is n W squared minus n log of W minus lambda times rho lambda d lambda. But in this rho lambda, you just have to stick in the Wigner semicircular form, and you see the energies of cost of energies of order n, and this is the right large division function. And if you evaluate this integral, so you find this answer here. Okay, so let me just summarize again. So this is the picture. Okay, so you have the phase transition is precisely at the critical point at the edge. When W is bigger than √2, Wigner semicircle, it sticks to that. When W equal to √2, it just touches this semicircle. So here is what you will see if you zoom in here in this regime. you will see the Tracy-Widom distribution. But if you go to the left, order 1 fluctuation, then you see this, left, the pushed phase, basically. And this is what I call the pulled phase, okay? So these are the 2 phases, essentially.
What's the order parameter?
Yeah, good question. No, so the order parameter, there's no obvious order parameter here, okay? But the only one way you can think of this is that, the way I would think of this as a, discontinuity in the derivative of free energy, okay? So this is the sort of, definition of phase transition, if you like. But you can, analog of order parameter will be the pressure. So you see this del phi, del W, okay? So if I take the first derivative with respect, so this is the wall. So when you push the wall, so the derivative of free energy, so that's like the pressure or force, basically, okay? So the force is non-zero, and then it becomes zero, basically.
Because it looks like it's the density against the wall.
Yes.
So it looks like on the left phase, you have this large density against
Right,
the wall.
right.
On the right phase.
Exactly. There's, on the right phase, the wall doesn't feel any pressure, right? It doesn't have to do any work in pushing, okay?
What I'm trying to see is what's the density.
Density of what?
To me, loosely speaking, I see a difference in the density close to the wall.
Yes.
It's finite, it's C.
So till W equal to root 2, it remains semicircle, okay? When W is strictly less than root 2, it changes. That's the sort of thing, okay?
So what I'm saying is, it looked to me that it was an order parameter. You divide by n squared. It's finite on the left, 0 on the right.
Yeah, I would not say it's order parameter. This log of is just a free energy, basically. So free energy, see, any phase transition, I don't have to always look at the order parameter. I can just look at the free energy, okay? So I look at the free energy and I see the, non-analytic free energy. That's the definition of phase transition, if you like, okay? And the, closest analog of order parameter is precisely this pressure, that you can feel that this is non-zero on this side and 0 on the other side. Okay. So to summarize the picture, so I'm just looking at the PDF of lambda max. So there is a typical fluctuation around root 2, which is given by the Tracy-Widom distribution here on a scale of n to the power minus 2/3. But if I go to the left, I have minus, this left large deviation tail, which is about speed n squared, and with a rate function phi minus. And on the right, it's e to the power minus n times rate function phi plus of W. And what you can check is that when W goes to root 2, as we saw here, that this goes like, 1 over 6 root 2 times root 2 minus W cube. So if I come from this side, okay, as I approach, if I make the W very close to root 2, okay, so then I'm approaching the, the left asymptotic tail of Tracy-Widom, because Tracy-Widom is on a scale of n to the power minus 2/3. So this regime here is like on a scale of n to the power minus 2/3, I have to look at minus infinity on the left. And there it was going like e to the power minus x mod x cube, and that actually matches with the small, W minus root 2 behavior, this cube here. And you can see that this prefactor, you can check that this prefactor here is there to ensure exactly the perfect matching, smooth matching with the Tracy-Widom left tail. And similarly here, if we approach W root 2 from the right, this right tail behavior matches with the right tail behavior of the Tracy-Widom on this side. Okay, so we have a fairly complete picture of the full distribution and not just the typical fluctuation. And you see it's very different from the coin tossing example, the toy example. There it was only one smooth function and with quadratic behavior at the top, with the Gaussian distribution, and you have a one large deviation tail which is symmetric and smooth. But here it's certainly non-smooth because of the behavior of n square and n on either sides. So it's highly asymmetric, and this is because there's a sort of phase transitions involved there. So basically the Tracy-Widom distribution you can think of as a finite size crossover function, finite by large n, connecting the free energies on the 2 sides. Okay, so that's the sort of picture. And okay, so let me just summarize and just, okay, as I said, so this is I'm just plotting the cumulative distribution. So again, this blue part here is the Tracy-Widom when you are going through this root 2. On the right, you have, here is cumulative, so it goes like 1 minus e to the power minus n. The previous one was, just a PDF. And on the left side, you have this. But this is to leading order. You can actually calculate you can ask what are the correction terms here on these sides, okay? And, okay, so this one actually we computed with Gaito Boro and Bartsuena and Celine Nadal, who was my PhD student. So, more or less fairly lot of things are known here. And so then after this, this large deviation calculation, so then you can actually apply to many other different problems, as I said, in the glassy system, which I talked about yesterday. And also recently there have been a lot of work on the random Gaussian surfaces, where you don't use the Hessian model, but you actually use a Gaussian model. But it turns out that there also, you need this large deviation function to compute the statistics of stationary points. String theory and cosmology I mentioned. And recently, it has been also used in this random polynomials and random words problem and so on. Okay. So now let me just elaborate on this third order phase transition. So as I said, that this is just the, if I look at on the left side here, so there is a finite n square. So this is the energy cost in pulling the gas. And if we take the log of this, which is just the free energy difference between the two sides, so that free energy difference goes like √2 minus cube here, as W goes to √2 from the left side, and it's 0 if W is on the other side. Okay, and so what you see is that this, this free energy difference, so it's 0 on this side. So I'm plotting. Okay, now I'm plotting just log with this guy. So this is 0 on this side, and phi minus of W on the other side. Okay, so and what you see is that the third derivative of the free energy is discontinuous, because here it's finite on the left side and 0 on the right side. Okay, so this is the definition of the third order phase transition. The third derivative of free energy is so it's not like the usual second order phase transition where you have a diverging correlation length and things like that. Here, there is no such thing. Here it's actually more like these two phases are like the strong coupling and the weak coupling phases. So again, just to tell you what the two phases are. So this is this critical point where Tracy-Widom is hidden over this critical point, and you have the left and right tail. So what is the left phase? So left phase is the strong coupling phase, because when you push this, this wall, if you enforce this constraint, all the charges have to, reorganize to give you a different density. Whereas on the right side, it's just one charge which is being pulled out of the sea. So here it involves a collective degree of freedom, it leads to reorganization of all the charges, whereas here it involves just one single guy, one single degree of freedom. Okay, so that's why it's called weak coupling, and this is a strong coupling phase. And so it's like, imagine that on a highway you are driving a car, and if you are the front car, and so you have an empty space in front of you. Now, if you want to, go forward, it's very easy. You just drive, you accelerate, and you go away. Okay, so that's the weak coupling phase. You don't have to bother with these guys, okay, behind you. But if you want to back up for some reason, then it's a problem, because if you have to back up, then everybody has to back up. Okay, so it involves everybody, all degrees of freedom, and so this is the strong coupling phase. So these are the two phases, and there's a transition between them. And Tracy-Widom is just this, crossover function that connects these two phases. Okay. So you can associate Tracy-Widom as a universal finite size crossover function across a third order critical point. Okay, so that's the sort of message. Now, the third order phase transition actually first appeared in a completely different context in the 80s in this famous paper by Gross-Witten and independently by Spenta-Wadia, who happens to be now the founding director of ICTS. So they were the first to, so they were studying sort of a large and lattice gauge theory in 2 dimensions. So it's the Young-Mills gauge theory in 2 dimensions with Wilson action. I'll not go into the, describe you what the Young-Mills gauge theory is. But, for us statistical mechanics, it's a very simple model. So imagine that you have a square lattice, and on each link of this lattice, you put an n by n unitary matrix, okay? So like this. And then you write the Wilson action. So it's like partition function. This is like the energy or action, if you like. So the action is just you take the product of these unitary matrices across each placket. So P is a placket. You take the product and you take the Hermitian conjugate of that, meaning that going in the opposite direction. So and then you take the trace of that object, and then you sum over all plackets. Okay. So this is called the Wilson action of the Young-Mills gauge theory in 2D. Okay, and this parameter G here is what is called the coupling strength. Okay, and the N here is the size of the unitary matrix. It's the n by n matrix. Okay, so I'm not going to explain why this is interesting to high energy physics, but they studied this, and then they had a phase diagram of this model as a function of, so on the y-axis you have 1 over n, And on the x-axis, you have the, let's say, inverse coupling 1 over g. Okay? So then, in the strictly in the n going to infinity limit, that means if you're on this line, as you vary this parameter g, there is a transition from a strong coupling phase to weak coupling phase. So this is when g is small. So this is called the strong coupling phase. This 1 over g square is large. And this is the weak coupling phase. Okay? I'm not explaining you what they mean by weak and strong phase because that will take time. But what happens here is when n is finite, is that you go from the strong coupling phase to weak coupling phase, but there's a crossover, finite size crossover. And this is what this string theory is called the double scaling regime. Okay? And so this double scaling regime, but actually, I mean, for us, it's just a single scaling. I mean, it's just, g goes to gc and n goes to infinity. So strictly in the n going to infinity, you have a sharp phase transition, and they showed that this is a third order phase transition, okay? And for finite n, you just have a crossover. And, what we have here is exactly the same picture, phase diagram, if you like. So what I'm plotting here, my control parameter is this w, the location of the, the lambda max. And again, I plot 1 over n. So when n goes to infinity, so you have a sharp phase transition from the pushed phase, which is the analog of the strong coupling phase. And then there's pulled phase, which is the analog of this weak coupling phase. Okay? And we have exactly same third order phase transition. But here, in our probability context, we know that this is the Tracy-Widom function. And if you go back and, analyze these papers, you realize that, here also is exactly same Tracy-Widom function as a crossover function. So, see, here there's no probabilistic interpretation of that. But if you, if you look at the crossover function that connects these two phases, which was actually studied by them, but, they didn't have a probabilistic interpretation. And you find that this is, precisely it satisfies the Pond-Levy equation of Tracy-Widom, these things. So this universality of Tracy-Widom is precisely because it is a finite size crossover function at a third order critical point. This is what, our conclusion is. And the mechanism in all these problems is precisely that. So you have a charge density which vanishes as a square root, and then you are, bringing, you are doing something to your system such that the gap between the density and the wall, the gap vanishes. So in the Young-Mills problem, in the Witten-Gross model, if you take the coupling parameter G goes to GC, what they showed is that there's some gap vanishes, okay? And it turns out that the gap vanishes exactly like the way as it happens here. And then if you, close to the critical point, if you zoom out and look at the crossover function, so in their case also it is the Tracy-Widom function. It was in the 80s, much before Tracy-Widom was discovered, okay? So this sort of, basically shows that indeed one of the reasons for the universality of Tracy-Widom distribution is precisely this mechanism. There is a phase transition associated with it, and Tracy-Widom is just a crossover function, finite size universal crossover function. All you need is that there should be some, some finite charge density which should vanish as a square root singularity, and the gap should somehow vanish. Okay. So in how the gap vanishes is different in different models, but the crossover function is universal. Okay. So this is the sort of conclusion, and this is sort of so the fact that we saw the same mechanism in many different models. So I'm not going to give you the details. We looked at the Wishart matrix. This is the covariance matrix. And again, typical distribution was found by Tracy-Widom in Johansson and Johnston. And we looked at the large deviations. We calculated the exact rate functions with Pierre Paolo Vivo and Origol Bohigas. And as I mentioned, in large N gauge theory in 2D. Then, more recently in the information theory, like the multiple input, multiple output channel capacity, this is like a linear statistics of this random matrix problem. I didn't discuss in detail. But here again, you find the same third order phase transition. As I mentioned, the complexity in spin glass models, random tiling. So, many, many different models, you see this third order phase transition, and you see an associated Tracy-Widom distribution. Okay? So we looked at, we studied, 4 different problems. I don't have time to talk about it. This conductance and short noise in mesoscopic cavities, entanglement entropy, the vicious Walker problem, and there's a wigner time delay problem in quantum dots and so on. And more recently, cold atoms and height distribution, KPZ, 1D plasma that Anupam talked about yesterday, and then this Ginniber ensemble in RMT and so on. And so with many collaborators, so let me just acknowledge them. So the main conjecture is, what we have gathered over the years now, over the last 10 years or so, is that wherever Tracy-Widom distribution occurs, there is an underlying third order phase transition. Okay, the reverse may not be true. I mean, if you have a third order phase transition, that all third order phase transitions, their the crossover function is Tracy-Widom, that we don't know. I mean, we cannot prove that, but if you see a Tracy-Widom distribution somewhere, which means that you should look for an underlying third order phase transition. Okay, and that actually gives a much better picture of the physics. That it's always associated to a phase transition point. Okay. And as I said, you can find some reviews of some of the little bit older work because it's rapidly evolving field, and in this review. And okay, last thing I just wanted to show you an experimental this thing. So this was from the Wiseman group by Neil Davidson, and this is the Wishart case. It's not the Gaussian random matrix. So they have the coupled laser, which is the following. So I mean, again, very briefly. So you have some cavity here, and you have the fiber laser wires basically, and you send lasers, and this you can think of this as an incoming, linear combination of incoming plane waves. So they come here and then they get mixed up essentially inside this quantum cavity basically, and then you look at the output. So it's like a scattering problem. You have a bunch of things which are coming in and gets interacted here, gets mixed up here, and then something goes out. So you have in all the random matrix thing, this is the general picture. So you have, for example, in the wireless communication network, you have these, incoming signals and there's these outgoing signals, and then something happens, it gets mixed up between here. So you can think of this quantum dot problem also. You can, send electrons, they move to the inside the cavity, and then they do scattering, random scattering, and then they come out. So the same picture basically, okay. And what they can measure is what is called the combined output power, which you can show that it's directly related to the largest eigenvalue lambda max. And they can actually measure the histogram of lambda max. Okay, so by looking at this detector by measuring the output power, and this is what they find. So what you are plotting here is the PDF of lambda max on a log-log scale, and so these circles here are okay. Ignore this picture; this is just experimental setup. So these pink circles here are the experimental points, and this red curve here is the Tracy-Widom distribution, okay? And we are plotting here on a scale of order 1. So what you see is that, near the center, Tracy-Widom works very well, but when you go to the large deviation regime, it no longer works. And this blue dotted curve is our left large deviation function, and the green dot dashed curve here is the right large deviation function. It's quite amazing. They can actually measure probabilities of order 10 to the power minus 6 in this experiment, okay? And so, yeah, I'll just finish. And if you go zoom out, this is, remember, this is the regime of order n to the power minus 2/3 fluctuations. So suppose you zoom out here and you just plot it on a scale of n to the power minus 2/3, and then you see a perfect matching with the Tracy-Widom distribution. Okay? So this is the sort of, the general picture. So let me just finish by acknowledging my collaborators and students and postdocs. So Aurelia Graves and Bertrand Lacroix, who is here, and then Anupam was a postdoc at LPTMS, and now he's a faculty member here at ICTS, and okay, several other people who are here. Okay, so thank you very much for your.
I'm curious by something you mentioned in the list.
Yes.
You had these random tilings.
Yes.
I can't read the paper, of course, that you quoted, but can you say something about how it appears there?
Yeah, random tiling models. So random tiling models is basically, okay, so, so people have looked at this combinatorial problems so these are all related to, again, this KPZ type of problem, basically. So this is, the directed polymer and things like that. So you can ask, how many ways I can tile a given surface, okay? And so they take this, what's called the Aztec diamond. I mean, I can't draw it on this thing. And you ask, how many ways can I tile this surface, okay? And so you can actually find out this, calculate this number exactly by using transformatrix techniques and so on. And what you find is that, again, there's a strong coupling phase where you can actually, when you pack all these diamonds in a particular way, and then the other side where you have a free phase, basically. So this is the tiling. I'm not giving details, but so. Yeah.
Yeah, well, that's a question I was going to ask. Yeah. Whether these ideas generalize to higher than one dimension, and this is exactly what you're showing, is what you're mentioning there.
To higher dimensions.
Yeah.
Yeah. So, okay, simplest way to think of higher dimensions is actually if you take the 2D Coulomb gas, which is the Geneva ensemble. So if you take an animatrix and you don't impose the symmetry that is real symmetric, okay. So you just take Gaussian for each element, irrespective of the independently, for all the elements. So now the eigenvalues will be complex, okay. So this is called the Geneva ensemble, and the complex eigenvalues will be on a unit square, okay. Unit circle, on a unit disk basically. That's the analog of wigner semicircular law. And you can ask, okay, I look at the largest, the particle which is furthest, and I ask for its distribution, okay. So what happens is that, you don't have the, Tracy-Widom distribution. There it turns out it becomes a Gumbel distribution, okay. But if you look at the, left large deviation tail, which means you have to compress this gas there, and again you see a third order phase transition, essentially. Okay.
Even if the crossover function is different?
Yeah, that's what I said. All third order phase transition does not mean that the Tracy-Widom is the crossover function. Okay.
So the nature of the transition is universal, but the crossover...
That's right. So third order is, in some sense, much more ubiquitous than the Tracy-Widom itself. Okay. Now, of course, it's sort of, it will be nice to understand this that, suppose you find a third order phase transition, so you find the crossover function. What are the, what is the sort of, what are the classes, universality classes, for instance? Okay, this is not known. And also, what would be nice is to develop some kind of renormalization group thing, to fixed point picture or something to classify these different crossover universality classes within the third order phase transition. Okay. So I only know of two examples. So one is, as I mentioned, this the complex case, if you look at this object. And the other is what Anupam mentioned in his lecture yesterday, 2 days back, which is if you look at the 1D Coulomb gas, okay. So again, you see a third order phase transition there, although the crossover function is not Tracy-Widom, but it's this non-trivial function that you was talking about, okay. So it's a different function, okay.
So some of these exclusion processes also have third order, right? And not all of them have to be Tracy-Widom, I guess.
Yeah. So sure, no, definitely. I think to me, third order phase transition is sort of much more universal than Tracy-Widom itself. Okay. There seems to be a wide class of third order phase transitions which do have Tracy-Widom distribution, but there are others. Okay. So
just to connect to 2 days ago.
Yeah.
So in that case, it was the linear potential.
Right. So it was just if you do the same problem, you just replace this log.
Yeah, with a linear potential.
Yes.
So what changes is a crossover.
Yes. So crossover function. So there, what happens is that the
We're starting to ring. But, quickly, maybe.
Huh? Sorry.
Well, explain quickly, but my coffee.
Yes. Sorry. Yeah. Very quickly. Okay. So there, what happens is that analog of wigner semicircle is just a flat distribution. Okay. So lambda max is centered around this, let's say, +1, okay? And you have this tail. And so you have this left tail, you have the right tail, which have, again, similar behavior. And in between, you have, some scaling function of n times, w minus 1 times n. Okay. So these are the three regimes. So again, this regime, there's this regime, and then there's this regime. Okay? But this function here is no longer Tracy-Widom function, but it's this, this sort of more complicated function, basically. But the point is that this thing here, this phi minus of w, it still, goes like w minus 1 minus w cube as w approaches to 1 from the left side. Okay. So it still has a third order phase transition, but the scaling function is not Tracy-Widom. So there is a subset of, third order phase transition critical point where the crossover function is Tracy-Widom, but there are some other things. A wide class seems to be Tracy-Widom. Now, how to characterize which third order phase transition will have Tracy-Widom distribution, that's not clear. But the reverse is true. If you see a Tracy-Widom, there has to be a third order phase transition. In fact, for us, when we saw this, and then when this work came out, recent work on the KPZ problem, that if you look at the height distribution in the KPZ that is given by the Tracy-Widom distribution, so you asked what is the third order phase transition there, and then you actually figure out what is the third order phase transition there. There is indeed a strong coupling and weak coupling phase, which is not obvious. When you just think of the KPZ problem, okay.
But in that case, you have an order parameter, which is a, which is a height.
Well, I mean, it's not. I mean, here you can say. I mean, it's not. Height is not really order parameter. So there you look at the probability distribution of the height, and but it's not an order parameter. No, it's not an order parameter. So. Sorry, Rob's coffee is getting thing we can probably discuss outside. So in the KPZ problem, what happens, the analog of this is that phi minus of h over t, and here you have this h over t to the power 1/3. It's exactly similar picture. And e to the power minus t, phi plus of h by t. So I'm looking at the height function, and I'm looking at a particular point in space, and I'm looking at the height, and I'm looking at the distribution at time t. Okay. So then, typical height fluctuation around its mean is t to the 1/3, and you again see Tracy-Widom distribution. But if you say what is the probability that height is much less than its average value, okay, on a scale of order t, then it's actually to the power minus t square. So the t is like the analog of n, if you like. Okay.
Yeah, so sorry, I really, rather than the KPC problem itself, I meant the Brownian excursion. So
Okay.
also have this.
That also have this, yes.
Written about this, right?
That's right, yeah. So.
Okay, either one more quick question or everything over coffee. Coffee, I think.
Yes.
9:30 we meet again here.